Hi everyone, this is my first math video. I'm doing this to celebrate a Pi Day, which is this date, okay, March of 14, 2013. I'm going to prove the Wallis product for pi. Let's get started. So we have to examine this interval, which is 0 from pi sine raised to the power of nx dx. For what? For any integer n. Okay. So I will let I of n to be this interval. I will be this integral, and then we write integration from 0 to pi and sine raised to the n minus 1 x sine to the x dx. And then I will apply the integration by part. Okay, integration by part. So I will let u to be sine raised to the power of n minus 1 x. So we're going to have du. What is du? Du is going to be this derivative. It's going to be the derivative of sine raised to the power of 1. It's going to be n minus 1. Okay? Sine raised to the power of n minus 2x, and derivative of derivative of sine, so it's going to be cosine of x. Okay? So I will let dv to be sine of x dx. So what happened to v? V is going to be n, so it's going to be the integration of sine x. So it's going to be minus cosine of x. Okay? So what do we have here? From this right here, we will apply integration by part. Okay, so here is the formula of integration by part, which is going to be integration of u dv equal to uv minus integration of v du. Okay, so now this term is u and this term is v. So what happened to this term is dv. All right, applying integration by part, we will have this term. So we're gonna have uv. U is going to be this one, sine raised to the n minus 1 x. V is here, minus cosine x. Okay, minus cosine x, so it's going to be minus cosine x from 0 to pi. All right, and then minus integrate from 0 to pi v. What is v? V is minus cosine, right? Minus cosine of x. Okay, and du is this term. Du is going to be n minus 1 sine raised to the power of n minus 2 x cosine x dx. Okay, so what is this term right now? We know that sine of pi is 0 and sine of 0 is 0. So this term turns out to be 0. So it's going to be 0 here and this one. Okay, this term is become n minus 1 of, and then integration from 0 to pi. Okay, cosine square x sine raised to the n minus 2x dx. Alright. According to trigonometric identity, what happened to cosine square? Cosine square is going to be n minus 1. Sorry, cosine square is going to be 1 minus sine square x times n raised to the n minus 2x dx. Alright, so it's going to be n minus 1 integration from pi, distribute this term. Okay, so it's going to be sine raised to the n minus 2x dx plus n minus 1 integration from 0 to pi sine raised to the n x dx. Okay, according to what we given here, this is in, right? In is integration from 0 to pi of sine raised to the nx. So this one right here, this integration here is going to be x n minus 2, in minus 2. This integration is going to be I of n. Okay, so now we will have in equal to n minus 1 times in minus 2 plus n minus 1 times in. So I will write down in terms of in minus 2. Okay, so it turns out to be, move this one to the right, to the left hand side. It's going to be in minus n minus 1 in equal to n minus 1 times n minus 2. Okay, so it turns out to be, what does it turn out to be? Something wrong here. I think we have something wrong. Minus sign here. Okay, minus sign, right? Minus sign, so it's gonna be plus sign here. So it's gonna be n times in equal to n minus 1 times in minus 2. Okay, so in is going to be n minus 1 over n times in minus 2. Okay, right now it turns out to be in over n minus 2, which is going to be n minus 1 over n. Okay, so this one I will call it star. Now what next? Next thing I want to do is to calculate I0 and I1. So now, what is I0? Okay, I0, plug in 0 into this term, is obvious, it's going to be 0. Okay, so it's going to be 0 to pi sine of 0 x sine raised to the power of 0. Okay, so it's going to be integration from 0 to pi dx, which is x from pi to 0, which is going to be pi minus 0, which is pi. Okay, and I of 1, what is it? I1 is going to be integration from 0 to pi sine raised to the 1 x dx is going to be integration from 0 to pi sine of x dx. Integration of sine x is minus cosine x from pi to 0. So it turns out to be minus cosine of pi minus cosine of 0. Okay, cosine of pi is -1. This term is -1. This is 1, right? Cosine of 0 is 1. So it turns out to be -1, -1, -1. So it is 2, okay? So it is 2, so I call this is equation 1, and this is 2. Now we have I0, which is pi, and I of 1, which is 2. Now, what about I2, I3, I4? Okay, so I have to I have to split into 2 cases. Okay, so for n, for an integer, for a positive integer n, okay, there are 2 cases. The first case is n is even, and n is odd. Let's start with n. Let's start with n being odd, n being even. What happened? So we gotta have, okay, so there exists integer k, positive integer k, such that n equal to 2k, okay, by definition of even number. So what happened to this equation from this equation? Okay, so we plug in n equal to 2k into n. So we gotta have I of 2k over I of 2k minus 2, okay, which is 2k minus 1 over 2k, okay, and then I gotta write I of 2k is gonna be I of 2k equal to 2k minus 1 over 2k times 2k minus 2. All right, okay, this is equation A. Next, when n is odd, what happened when n is odd? So we gotta have integer k, a positive integer k, such that n equal to 2k plus 1. Okay, so what happened to equation store? Equation store becomes, what does it become? Right here, equation store, plug in k plus 1 into n. So we gotta have I of 2k plus 1 over which one? I of 2k minus 1 equal to what? Substitute 2k plus 1 into n, 2k plus 1, so it's gonna be 2k over 2k plus 1. Okay, then it turns out to be multiply both sides by this term, so we're gonna have I of 2k plus 1 equal to 2k over 2k plus 1 times I of 2k minus 1. This is equation B. Now, let's take a look at at even value. Okay, take a look at this one, even value. I will calculate this term by using recurrence relation. So for even value, I 2n, I gotta write 2n. Okay, so I of 2n, what happened? It's going to be integration from 0 to pi sine of 2n x dx, which is 2n minus 1 over 2n times I of 2n minus 2. And plug in this term into here. Okay, so we're going to recur, how do you say it? Recurrence relation. What happened to this term is going to be 2n minus 1 over 2n. So it's going to be 2n minus 3 over 2n minus 2 times I 2n minus 4. Okay, and then we plug in all the way to the last value. Okay, we use a all the way to the last value. We used recurrence relation, so we gotta have 2n minus 1 over 2n. Okay, next term is gonna be 2n minus 3 over 2n minus 2. Next term is gonna be 2n minus 5 over 2n minus 4. Okay, this term is decreasing, right? So it turns out to be, it's going to be odd number. So it's going to be go to 5, 6, right? Okay, 3, and then 4, and then 1, 2. Okay, now what's next? The last one is going to be, so the last one, in this case, if n is 1, what happened? When n is 1, or we plug n into, we plug k being 1 right here. So you're going to have I of 0, right? It turns out to be I of 0 here. Okay, then it turns out to be I of 0 and this term. What is I of 0? I of 0, what is it? Where am I of 0? It's pi, right? According to equation 1, it is pi. So it turns out to be, okay, I of 2n is going to be pi, and this term, what is it going to be? It's going to be pi, okay, from k equal to 1 to n, right? And 2k minus 1 over 2k. Okay, this is I2, right? For the case where integer is an even number. So this equation, this is equation 3. Okay, equation 3. Now let's calculate the value of I for odd value. Now, for odd value, what do we have? For odd value is going to be I of 2n plus 1. So So it's going to be I of 2n plus 1, which is integration from 0 to pi sine raised to the power of 2n plus 1 x dx. Okay, so what is this term? This term, according to this equation or recurrence relation, right? Let me copy this one. Recurrent relation B. Okay. So it turns out to be 2n. Okay. Just plug in n right here. 2n over 2n plus 1 times I of 2n minus 1. Alright. So what is this term here? It's going to be 2n over 2n plus 1 times 2n minus 2 over 2n minus 1 I of 2n minus 3. Alright. And now, what's the next term? Okay. It's increased by 2, right? So the next term is going to be 2n minus 4 over 2n minus 3. So it turns out to be 2n over 2n plus 1 times 2n minus 2 over 2n minus 1 times 2n minus 4 over 2n minus 3 times, which one? I of 2n minus 5. Okay. Let's use this recurrence relation all the way to the last term. So we're going to have, okay, let me copy this term. So the next term is going to be all the way to 6 over 7. Next term is 4 over 5. Next is 2 over 3. And I of 1. Okay. Why is I of 1? So when n is 2, what happened? When n is 2, okay, is 2 times 2, which is 4, right? And 2 times 2 plus 1 is 5. And 4 minus 2, and 4 minus 1, which is 3. And this one is 2 times 2 minus 3, it is 1. So it's going to be I of 1. Okay? Then it turns out to be I of 1. Okay? What is this term here? Here. So we write down in terms of big pi. The big pi is this product. The product of 2k over 2k plus 1 from k equal to 1 to the n. Okay. Now, this is I of 2n plus 1 equal to this term. Okay. Here, and this is equation 4. Now, what I want to do next, once you have this term, the value for even value and for odd value, next thing you want to do is to observe the value of sine. Okay? Observe the value of sine. So we have sine raised to the 2n plus 1x, right? And we observe sine to the 2nx and sine of 2n, sine raised to the power of 2n minus 1x. Okay? So we know that sine is greater than or equal to 0 and less than or equal to 1 for which value of x? For x greater than or equal to 0, less than or equal to pi. So what happened here? What happened? I want to write down this term. sine raised to the power of 2n plus 1 x is going to be sine of raised to the power of 2n times sine x. And sine x is less than 1. Less than or equal to 1. What happened to this one? So it's going to be less than or equal to sine of 2n x, sine raised to the power of 2n x times 1, which is turns out to be sine raised to the power of 2n x. And what next? Sine raised to the power of 2n, which is sine raised to the power of 2n minus 1 x sine x, and sine x less than or equal to 1. So it's going to be sine raised to the 2n minus 1 x times 1, which is sine raised to the power of 2n minus 1 x. Okay? So we're going to have sine raised to the power of 2n plus 1 x less than or equal to sine of raised to the power of 2n x less than or equal to 2n minus 1 x. For which value? For x greater than or equal to 0, less than or equal to pi. Okay? And then we integrate this one from 0 to pi. We integrate all of this inequality. Okay? So we're going to have this integration here and this integral, right? The x dx like this, which means that this term is I of 2n plus 1 less than or equal to this term. This is I of 2n less than or equal to I of 2n minus 1. Now, what do we know next? Okay. We know that this integral is greater than 0. It's always greater than 0. Why? Because sine is greater than 0. Okay? So all of these integration must be greater than 0. Once this one is greater than 0, okay, I of 2n plus 1 is greater than 0. We can divide both sides. We can divide this inequality by I of 2n plus 1. So we're going to have, so what do we have here? We're going to have 1 less than or equal to I of 2n over I of 2n plus 1 less than or equal to I of 2n minus 1 over I of 2n plus 1. Okay? Now, what is this term and this term? We can go back to this recurrence relation B here. Okay, what do we have here? What happened to the denominator? Okay? What happened? What happened to the denominator is going to be I of 2n minus 1 over this term is this one is 2n over 2n plus 1 times I of 2n minus 1. Okay? Right? So what do we have here? These will be cancelled. So it turns out to be 2n plus 1 over 2n. So what next? Where is the pi? Okay? Where is the pi? So what I'm going to do? we will use squeeze theorem. Okay, we will use squeeze theorem. So by squeeze theorem, what do we have here? As n approach to infinity, okay, this one is going to be n to infinity of I of 2n over I of 2n plus 1 less than or equal to this one, right? This term, okay, is going to be the limit as n approach to infinity of 2n plus 1 over 2n. This is obvious, which is 1. This limit is 1, okay, and this limit remain the same. It remains the same, and this one will be, this limit is 1, right? Okay, why is it 1? So when we factorize n, so you're gonna have n times 2 plus 1, 2 plus 1 over n, right? Over 2n. So this n will be cancelled. When n approaches to infinity, 1 over n approach 0. So it turns out to be 2. Okay? Oh, sorry. It turns out to be 2 over 2, which is 1. So it's going to be 2 plus 1 over 2, which is 1. So it's going to be less than or equal to 1. Therefore, by squeeze theorem, it implies that this limit is equal to 1. Okay? This limit is 1. Now, what can we do next? Okay? Let's consider this term. Let's consider this term. We will use equation 4 and equation 3. Okay? Equation 4 and equation 3. Here. Alright. So let's calculate this term. Okay? So by 3 and 4, what do we have? So I of 2n over I of 2n plus 1. Where is the pi? The pi is coming here. Okay? So it's going to be, okay, let me copy this one. This is numerator over the denominator here. Okay? Right? So what happened? According to the property of this big pi, we're gonna have pi over 2 of big pi k equal to 1 to the n, okay, of this term times this one. This term is going to be the big pi from k equal to 1 to n, 2k over 2k plus 1 raised to the negative 1. Okay? Raised to the negative 1, so we're going to have pi over 2. Okay? I will copy this term. Right? Copy this term. So it turns out to be 2k over 2k plus 1 raised to the negative 1. Okay? Now, it turns out to be, let me copy this term. So it's going to be pi, big pi from k to 1 to n of k plus 1 over 2k. Okay? By the property of this big pi. Okay? So it's going to be pi over 2 of times k equal to 1 to the n of 2k minus 1 over 2k times 2k plus 1 over 2k. Alright? That's what we have right now. And then take the limit both sides. Okay? This term is this one. Okay? We use the limit as n approach to infinity. What do we have here? We're going to have pi over 2 as limit, pi over 2 and limit of this term as n approach infinity. Okay? And this term is going to be, what is it going to be? It's 1 right here. Okay? We know that it is 1. So it's going to be pi over 2. If this is n, if this is limit, this is the limit as n approach infinity is going to be big pi when k equal to 1 to infinity and this term. Okay, now we are almost there. We have this pi right here, right? Pi over 2. Okay, so pi over 2 is going to be this term. Okay, it's going to be this term raised to negative 1. So we will have this pi. Okay, so pi over 2, which is going to be, which is k, this product, this big pi from k equal to 1 to infinity, which is 2k minus 1 over 2k times 2k plus 1 over 2k raised to the negative 1. Okay, so it turns out to be 2k over 2k minus 1 times 2k over 2k plus 1. So we're going to have the product for pi. Okay, we're going to have the product for pi. If you calculate this one, it turns out to be, let's start from 1. When k is 1, you're going to have 2 times 1, right? It's going to be 2 over 1 times 2 over 3. Okay, times, next term, k is 2. 2 times 2 is 4 over 3 times 4 over 5 dot 6, right? When k is 3, so it's going to be 6 over 5 times 6 over 7 and all the way and so on. So this is the product for pi proposed by John Wallis. Okay, thank you to watch this video. Feel free to subscribe my channel, everyone, and happy Pi Day.